Today, we are diving deep into the hidden senses of our technology. We're going to pull back the curtain and look at the fundamental principles that let our devices see, hear, feel, and even smell the world around them. How do they turn physical reality into digital information? Let's find out. So let's start with something you probably have right in your hand or in your pocket: your phone. I mean, you tap on it, you swipe, you pinch to zoom. How on earth does this little slab of glass and metal know exactly what you want it to do with such perfect accuracy? And it's not just our phones, right? Think about your car's dashboard telling you your speed, or the thermostat at home that just knows when to kick on the heat, or even an automatic door that opens right as you walk up to it. It all kind of feels like magic, doesn't it? But it's not. It's all thanks to the invisible world of sensors. The real question is, how do they actually do that?
Well, the answer to all of these questions really boils down to this one single crucial concept: transduction. Now, it sounds super technical, I know, but the idea is actually pretty simple. It's the process of taking something happening in the real world, like pressure from your finger or heat or light, and converting it into an electrical signal that a computer can actually understand. You can think of it as the universal translator between the physical world and the digital one.
Okay, so to really get a grip on this, we're going to break it all down. We'll start with what I like to call the foundational four. These are the real workhorses of the sensor world, the ones that handle a ton of the tasks we rely on every single day. First up, we've got resistive transduction. The principle here is pretty straightforward. When you push, pull, or even just heat something up, its electrical resistance changes. It's kind of like electricity trying to run down a hallway. If you stretch or squeeze that hallway, it gets narrower and longer, making it harder for the current to get through. A sensor just measures that change in difficulty, that resistance, to figure out exactly how much force is being applied. Next, let's talk about capacitive transduction. Remember that smartphone screen we started with? This is the magic behind it. The screen has this invisible grid of conductive material. Your finger is also conductive, so when you bring it close, you actually change the electrical field, the capacitance between those grid lines. The phone's brain just pinpoints where that change happened, and boom, it registers a touch. It's the very same idea used to sense things like humidity or even pressure. So let's just pause for a second and compare these two, because they sound similar. Resistive is like a dimmer switch. As you change the material, you change how easily electricity flows through it. Capacitive is different. It's all about how something, like your finger, changes an electric field between 2 points. So one is about a change inside a material, and the other is about a change in the space between them. All right, our third foundational mechanism is inductive transduction, and this one is all about magnetism. Basically, when a magnetic object moves near a coil of wire, it messes with the magnetic field, and that changes the coil's inductance. This is absolutely perfect for measuring position with incredible precision, and without anything ever having to touch. A great example is an LVDT, which is a sensor used to spot teeny tiny movements in big industrial machines. And rounding out our foundational four is piezoelectric transduction. Honestly, this one is just so cool. There are certain types of crystals that when you squeeze them or apply stress, they literally generate a tiny voltage. It's a direct conversion of mechanical energy into electrical energy. And this is exactly how a microphone works. Sound waves are just vibrations in the air that put stress on a tiny piezoelectric crystal, which turns those vibrations into the electrical signal of your voice. Amazing. Okay. So we've covered the basics of how our tech can feel force, position, and vibration. But the world is so much more complex than that, right? What about all the other senses? How does technology see light, or feel heat, or even detect the presence of different chemicals in the air? Well, that brings us right to part two, the specialist senses. Think of these next transduction mechanisms as more tailored, specialized tools, each one designed to convert a very specific type of energy, like heat or light, into data we can use. First up for the specialists is thermoelectric transduction. This uses a really clever physics trick. You just join two different kinds of metal wire together, and then you heat one end. When you do that, a tiny voltage magically appears at the other, cooler end. And the bigger that temperature difference is, the higher the voltage. That simple, incredibly reliable principle is behind thermocouples, which are some of the most common temperature sensors on the planet. Now, how do we give our devices the sense of sight? For that, we use photoelectric transduction. This is how they see. When particles of light, photons, hit a special material inside something like a photodiode, they actually knock electrons loose, which creates an electrical current. More light means more current.
It's a beautifully simple principle that's the foundation for everything from the sensor in your camera to the automatic lights that turn on when it gets dark.
Next on our list is electromagnetic transduction. Now, this one is a direct application of a famous physics principle, Faraday's law of induction. All it says is, if you move a conductor through a magnetic field, you generate a voltage. It's actually the exact reverse of how an electric motor works. A tachogenerator uses this to measure rotational speed. The faster it spins, the higher the voltage it puts out. It's a super simple, direct way to measure velocity.
And finally, how does technology smell or taste? Well, that's where electrochemical transduction comes in. In this case, a very specific chemical reaction involving the exact substance you want to measure, like carbon dioxide or maybe an acid, produces a measurable electrical signal. So a CO2 sensor, for example, creates a current that is directly proportional to the amount of that gas in the air. This is, quite literally, technology's sense of smell.
So, we've just run through 8 totally distinct ways that technology can sense the world. And, this isn't just a random list of facts. This is a practical toolkit. It's what engineers actually use to decide how to build all the smart devices we rely on every single day.
The process is really logical. First, an engineer has to identify exactly what they need to measure. Is it temperature? Is it force? Light? Then, based on that need, they look at this list and choose the absolute best transduction principle for that specific job. A piezoelectric sensor might be great for vibration, but it's totally useless for measuring gas composition. And then finally, they design and build the sensor around that chosen principle.
And this quote from the source material really just says it all. This whole classification system, it's not just academic. It's the fundamental knowledge you need to build smart, responsive, and effective technology. Understanding how a device can sense is always the first step in creating a device that can sense. So the next time your phone responds perfectly to your touch, or your thermostat adjusts the temperature without you thinking about it, you'll know the secret. It's all about transduction. And it really makes you wonder, right? As our technology gets more and more advanced, what other senses are we going to engineer for it? What will our devices need to feel, or see, or even smell in the future?